It's late, and somewhere in the room you're sitting in right now, the air is doing something strange. Without your noticing, molecules are colliding, light is bouncing off every surface, and your brain is quietly, tirelessly turning all of that into the calm, ordinary scene around you. The walls look solid, the floor feels dependable, and yet, if you ask a physicist what any of that is actually made of, the answer gets stranger the closer you look. This is a story about that strangeness, not the kind that's designed to shock you, but the slower, deeper kind that shows up when careful people spend decades asking simple questions and refusing to stop at the first comfortable answer. Questions like, is the world really the way it looks? Is there a solid, fixed universe sitting out there, waiting for us to notice it? Or is something else going on? Something closer to a process than a place? We'll take our time with this. There's no need to rush toward a punchline, because there isn't one, not really. What there is instead is a long, patient unfolding of ideas, from the neuroscience of how your brain builds the world you experience, through the strange results of quantum experiments, out to black holes and the structure of space itself, and finally, to the question of what a conscious observer even is, and why some physicists think that question might be more central to reality than anyone expected a century ago. Let's start somewhere gentle, with you, and with the simple act of seeing, right now, whatever you're looking at, whatever colors and shapes are in front of you, your brain is not showing you the world directly. It's building a model of it. Light enters your eyes as patterns of electromagnetic radiation. Sound enters your ears as vibrations in the air. And none of that comes with labels attached. There's no little tag on a photon that says, this is red. Your brain has to do a huge amount of quiet, invisible work to turn raw physical signals into the smooth, continuous experience you're having right now. Take color. Physically, light is just electromagnetic radiation at various wavelengths. A wavelength around 700 nanometers doesn't contain redness in any physical sense. Redness is something your visual system produces when certain receptors in your eyes are stimulated in a certain pattern, and your brain interprets that pattern in a particular way. Different animals do this differently. Bees can see ultraviolet patterns on flowers that are completely invisible to us. Some birds have 4 types of color receptors instead of our 3, letting them distinguish shades we can't even imagine. And within our own species, some people experience color differently because of variations in their visual systems, including different forms of color blindness. The world doesn't come pre-labeled with color. Your nervous system produces it, moment to moment, as a kind of internal shorthand. The same is true of sound. Air molecules bump into each other in waves, and that's it. Physically speaking, there's no music in the air, no voice, no color of tone. All of that arises when your ear converts those pressure waves into electrical signals, and your brain assembles those signals into something you recognize: a car horn, a friend's laughter, a favorite piece of music. The experience is real in the sense that it's genuinely happening to you, but it's happening inside your nervous system, not out in the air itself. This isn't a philosophical trick. It's basic, well-established neuroscience and sensory biology. Your brain doesn't passively receive the world. It actively reconstructs a simplified, useful version of it, moment by moment, based on incomplete and noisy information. Now, one of the more interesting extensions of this idea comes from the cognitive scientist Donald Hoffman, and it's worth being clear about where this idea sits scientifically, because it's genuinely provocative and not universally accepted. Hoffman's core claim is that evolution doesn't shape our perception to show us the truth about reality. It shapes our perception to keep us alive and help us reproduce. Truth and usefulness, he argues, are not the same thing, and when they conflict, evolution favors usefulness every time. To test this, Hoffman and his collaborators built mathematical models using evolutionary game theory, simulating populations of virtual organisms that perceive their environment in different ways. Some perceive it accurately, tracking the true underlying structure of resources and dangers. Others perceive only a simplified set of cues, tuned purely to guide behavior that helps them survive without regard for whether those cues reflect reality accurately. Across a wide range of these simulations, Hoffman's team found that organisms tuned only for usefulness generally outcompeted organisms tuned for accuracy. In other words, in his models, seeing the truth was not an evolutionary advantage. Seeing what's useful was. Hoffman describes our perception using the metaphor of a computer desktop. When you drag a file into the trash icon on your screen, you're not interacting with the actual electrical structure of the hard drive underneath. You're interacting with a simplified visual interface designed to let you do something useful without understanding or needing to understand the vastly more complicated reality humming away beneath it. His argument is that our perception of tables, colors, even space itself might work the same way, a functional interface shaped by evolution that lets us act effectively in the world without showing us what's actually there. It's important to say clearly that this is a hypothesis and a contested one. Most cognitive scientists agree that perception is a constructed, simplified model rather than a direct window onto reality. That much is well supported, but Hoffman's stronger claim that our perception of space, time, and physical objects has essentially nothing to do with the true structure of reality remains a minority position, actively debated among philosophers of mind and cognitive scientists. Many researchers think perception, while simplified, still tracks real structure in ways that matter, because organisms that get too disconnected from the actual causal structure of their environment tend not to survive very long either. The debate is genuinely open, and it's one we'll return to later because it connects in surprising ways to some very strange results coming out of quantum physics. For now, hold on to the simpler, less controversial version of the idea, your everyday experience of the world, its colors, sounds, textures, even its apparent solidity is a construction. It's produced by your nervous system using raw physical signals as its material. That much isn't controversial at all. It's the starting point for almost everything that follows, and it raises a natural question. If your brain is constructing a simplified model rather than showing you the world directly, what is actually out there underneath the model? What does modern physics say about the raw material your brain is working with before your nervous system gets a hold of it? That's where things start to get genuinely strange, and where we'll spend most of our time tonight, because it turns out that when physicists ask that same question, using instruments instead of eyes and equations instead of intuition, they run into puzzles just as deep as anything in neuroscience. The world underneath the world, it turns out, doesn't look anything like a solid, waiting to be discovered place either. To understand why physicists started doubting the solidity of the world, it helps to go back to the very beginning of quantum mechanics at the start of the 20th century, because the story didn't begin with anyone trying to overturn reality. It began with a technical problem that nobody expected to be philosophically important at all. In the year 1900, the physicist Max Planck was trying to solve a very specific puzzle about how hot objects radiate energy, something called the blackbody radiation problem. The existing equations of classical physics predicted that a hot object should radiate an infinite amount of energy at very short wavelengths, which obviously isn't what happens in reality. Planck found that the only way to make the math match the actual measurements was to assume that energy isn't radiated smoothly and continuously, but in small discrete packets, which he called quanta. He treated this as a mathematical convenience at first, not necessarily a description of physical reality. 5 years later, in 1905, Albert Einstein took Planck's idea further and used it to explain something called the photoelectric effect, the way light striking a metal surface can knock electrons loose, but only if the light is above a certain frequency, regardless of how bright it is. Einstein proposed that light itself is made of discrete packets of energy, which we now call photons. This was a radical claim at the time because light had been understood quite successfully as a wave for roughly a century, ever since the work of Thomas Young and others in the early 1800s. Einstein was suggesting that light is somehow both a wave and a stream of particles, depending on how you look at it. Over the following 2 decades, physicists including Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and Louis de Broglie built out a full mathematical framework to describe this strange dual behavior, not just for light, but for matter as well. De Broglie proposed in 1924 that if light can behave like particles, perhaps particles like electrons can behave like waves too, an idea that was confirmed experimentally a few years later when electrons were shown to produce interference patterns, a signature behavior of waves. This is where the double-slit experiment becomes central to the whole story, and it's worth walking through slowly because almost everything that follows traces back to this one setup. Picture a barrier with 2 narrow parallel slits cut into it and a detector screen behind it. If you fire a stream of ordinary objects, marbles, say, through the 2 slits, you'd expect to see 2 bands on the screen behind, roughly lined up with the 2 slits, because each marble goes through one slit or the other and lands somewhere behind it. But if you fire something like electrons, one at a time, through the same setup, you don't get 2 bands. You get a whole pattern of alternating bright and dark stripes called an interference pattern, the same kind of pattern you'd get from 2 overlapping water waves. This is deeply strange because interference happens when a wave passes through both slits at once and overlaps with itself on the other side. Somehow, individual electrons, fired one at a time, minutes apart, still build up this wave-like interference pattern over time, as though each electron is somehow passing through both slits simultaneously and interfering with itself. Now here's the part that turned this from a strange curiosity into one of the deepest puzzles in physics. If you place a detector at the slits to determine which slit each electron actually goes through, the interference pattern disappears completely. Instead, you get the 2 simple bands you'd expect from particles going through one slit or the other. The simple act of gaining information about which path the electron took changes its behavior from wave-like to particle-like. This isn't a flaw in the equipment, and it isn't something that goes away with better instruments. It has been repeated with electrons, with photons, and even with larger molecules, up to complex organic molecules made of many atoms, and the result holds every time. Measuring which path a particle takes destroys the interference pattern. Not measuring it preserves the interference pattern. The particle seems to behave differently depending on whether that particular piece of information exists anywhere in the world. The mathematical framework that emerged to describe this, developed mainly by Schrödinger and Heisenberg in the mid-1920s, describes a quantum system not as being in one definite state, but in what's called a superposition, a combination of multiple possible states at once, described by something called a wave function. The wave function doesn't tell you where a particle is. It tells you the probability of finding it in various places if you were to measure it before a measurement happens. According to the mathematics, the particle doesn't have a single definite position at all. It has a whole spread of possibilities, weighted by probability. This raised an uncomfortable question almost immediately, one that's often called the measurement problem, and it's remained unresolved in the sense of not having a single agreed-upon answer for about a century now. If a quantum system exists as a spread of possibilities before measurement, what exactly happens during a measurement that picks out one single, definite outcome? The mathematics describes this as the wave function collapsing onto one specific result, but the equations themselves don't explain why or how that collapse happens, or what precisely counts as a measurement in the first place. The physicist who did the most to popularize one answer to this in the mid-1920s was Niels Bohr, working alongside Heisenberg in Copenhagen, which is why their general approach became known as the Copenhagen interpretation. Their view, roughly, was that it's not meaningful to ask what a quantum system is doing before it's measured. The wave function is simply the best available description of our knowledge about the system, and asking what really happens underneath it is not a well-posed scientific question. Physics, in this view, describes what we can observe and predict, not some hidden layer of reality underneath our observations. Not everyone found this satisfying, including Einstein himself, who spent much of the rest of his career uneasy with the implications of quantum mechanics, even though he had helped create the field. He famously argued in a series of exchanges with Bohr that quantum mechanics, while clearly making accurate predictions, must be an incomplete description of reality, missing some deeper layer of hidden variables that would restore a more familiar, definite picture of the world if we could only uncover it. For decades, this was treated as largely a philosophical disagreement, interesting to think about, but not something you could test in a laboratory. That changed in the 1960s, thanks to a physicist named John Stuart Bell, and the test he devised turned out to be one of the most consequential experiments in the history of physics. Before we get to Bell's work, it helps to understand the phenomenon he was testing: quantum entanglement. When two particles are produced in a way that links their properties together, for example, two photons emitted from the same source in a way that conserves certain physical quantities, they can end up in a special shared state. If you measure a property of one of them, say its polarization, you instantly know something about the corresponding property of the other, no matter how far apart they are. Einstein, along with physicists Boris Podolsky and Nathan Rosen, wrote a paper in 1935 pointing out how strange this was. If quantum mechanics were complete, measuring one particle would seem to instantaneously affect the state of a distant, separate particle, something Einstein called spooky action at a distance, and something that seemed to sit uneasily next to his own theory of relativity, which holds that no influence, and certainly no usable information, can travel faster than the speed of light. Their argument, often called the EPR paper, after their initials, was intended to show that quantum mechanics must be missing something, some hidden underlying variables that determine the outcomes in advance, so that no real, faster-than-light influence is actually needed. For almost 30 years, this remained a matter of interpretation since nobody had found a way to experimentally distinguish between quantum mechanics is complete and genuinely strange, and quantum mechanics is incomplete and there are hidden variables we haven't found yet. Then, in 1964, John Bell found a way. Bell showed mathematically that if the universe obeys what's called local realism, meaning that particles have definite properties before they're measured, and that no influence can travel between distant particles faster than light, then there's a strict mathematical limit on how correlated the measurement outcomes of entangled particles can be. This limit is now called a Bell inequality. Crucially, quantum mechanics predicts that entangled particles can violate this limit, showing correlations stronger than any local, realistic theory could ever produce. This turned a philosophical dispute into something you could actually go into a laboratory and test. Throughout the 1970s and 80s, a series of increasingly careful experiments were carried out to test Bell's inequality directly. The physicist John Clauser and his colleagues performed some of the earliest versions of these tests in the early 1970s. Then, in a set of landmark experiments in 1982, the French physicist Alain Aspect and his team measured the polarization correlations of entangled photons over a meaningful distance and found clear violations of Bell's inequality, matching the predictions of quantum mechanics rather than the constraints of local realism. For a while, critics pointed out that these early experiments still had loopholes, gaps in the experimental design that could, in principle, allow a hidden variable explanation to survive. There was the locality loophole, the concern that the two measurement devices might somehow be secretly communicating within the time available. There was the detection loophole, the concern that only a subset of particle pairs were successfully detected, potentially biasing the results. Closing all of these loopholes simultaneously took decades of technical refinement. By around 2015, several independent research groups, including teams led by Ronald Hansen in the Netherlands and others working with photons, succeeded in closing essentially all the major loopholes at once in what are now called loophole-free Bell tests. The results, once again, matched quantum mechanics and violated Bell's inequality, this time under conditions carefully designed to rule out alternative explanations. This body of work was significant enough that in 2022, the Nobel Prize in Physics was awarded jointly to Alain Aspect, John Clauser, and Anton Zeilinger for their experiments demonstrating the violation of Bell inequalities and for pioneering the field of quantum information science that grew out of this research. So what does it actually mean that Bell's inequality is violated? It means that at least one of the two assumptions behind local realism has to be given up. Either particles don't have definite, pre-existing properties before measurement, meaning measurement genuinely brings a specific outcome into being, rather than simply revealing something that was already there, or there is some kind of influence that connects distant, entangled particles in a way that isn't limited by the speed of light, at least not in the way ordinary causal signals are. It's worth being careful here about what this doesn't mean. It doesn't mean that information can be sent faster than light, which would violate special relativity. The correlations between entangled particles can't actually be used to send a message because the outcome of any individual measurement still looks random from either side. The strange correlation only becomes visible when you later compare notes about many results, and comparing notes still requires ordinary, slower-than-light communication. So the puzzle isn't about broken causality in any way that lets you send signals into the past or violate relativity outright. The puzzle is deeper and stranger than that. It's about what kind of a thing an unmeasured particle even is, and whether the correlations we observe between distant, entangled particles reflect some kind of connection that doesn't fit comfortably into our ordinary picture of separate objects sitting in separate locations. Physicists disagree about how to interpret this. Some, following a line of thinking descended from the Copenhagen interpretation, simply say that quantum properties genuinely don't exist until measured, and that's just a brute fact about how reality works at that scale. Others favor an interpretation called many worlds, first proposed by the physicist Hugh Everett in 1957, in which the wave function never actually collapses at all. Instead, every possible outcome of a measurement occurs, but in separate, non-communicating branches of reality, and what we experience as a single random outcome is simply the branch we happen to find ourselves in. Still others favor an approach called pilot wave theory, developed originally by de Broglie and later extended by the physicist David Bohm in the 1950s, in which particles do have definite positions at all times, guided by an underlying wave, but the theory has to introduce a very particular kind of non-local influence to match the experimental results, essentially building the spooky connection directly into its equations rather than avoiding it. There is no consensus among physicists about which of these interpretations, if any, is correct. All of them make the same experimental predictions in every case that's been tested so far, which is part of why the disagreement has persisted for so long. It isn't currently possible to settle the question with an experiment, only with argument, aesthetic preference, and philosophical commitment. What is agreed upon, because it's been tested so thoroughly, is that the world does not behave the way local realism says it should. Something about the classical, common-sense picture in which objects have definite properties all the time and only interact with their immediate surroundings has to give way. Exactly what replaces it is still being debated. There's another family of experiments worth sitting with for a while, because they push the strangeness of measurement even further than the basic double-slit setup into territory that seems to involve the order of events in time itself. In 1978, the physicist John Archibald Wheeler proposed a thought experiment called the delayed choice experiment. The idea was this: what if you could choose whether or not to measure which path a particle took after the particle had already passed through the slits, but before it hit the final detection screen? Wheeler wanted to know whether the particle would somehow know in advance to behave like a wave or a particle, or whether the later choice of measurement would still determine which behavior showed up, even though the particle was already most of the way through its journey. For a long time, this remained a thought experiment, difficult to realize with the technology available. But by the 1990s, physicists had developed techniques using entangled photon pairs that made a related and even more striking version possible, called the delayed choice quantum eraser. One well-known version of this experiment was carried out by the physicist Yoon Ho Kim and colleagues in 1999. Here's roughly how it works. A photon is sent through a double-slit setup, and its entangled partner photon is sent off in a different direction toward a separate set of detectors. Because the two photons are entangled, information about which slit the first photon passed through can, in principle, be recovered by looking at its partner. If the experimenters keep that which path information available, By routing the partner photon to a detector that preserves it, the interference pattern in the first photon's results disappears, just like in the ordinary version of the experiment. But if the experimenters instead erase that information by routing the partner photon through a setup that mixes the path information together so it can no longer be recovered, the interference pattern reappears, even though nothing about the first photon's actual journey through the slits has changed. The genuinely strange part is the timing. Because of how the experiment is arranged, the choice to preserve or erase the path information on the partner photon can be made after the first photon has already been detected on the screen. And yet, whether that first photon's individual detection event ends up contributing to an interference pattern or not depends on a choice made afterward, on a completely different photon. When physicists carefully sort the results after the fact, separating out which detections correspond to erased information and which correspond to preserved information, they find the interference pattern in one group and not the other, split out from what looked like a single jumbled set of data at first. It's important to be precise about what this does and doesn't show, because it's easy to describe it in a way that sounds like it violates cause and effect, sending information backward in time. It doesn't. No signal or usable information travels backward, and the experiment is fully consistent with the ordinary flow of causality once you account for the fact that comparing the two sets of results, the screen detections and the partner photon detections, still requires ordinary communication, which can only happen after both measurements are complete. What the experiment does show is that quantum correlations don't respect a simple story in which the photon decides whether to be a wave or a particle at the moment it crosses the slits and sticks with that decision from then on. The pattern that shows up depends on the full experimental context, including choices made elsewhere, and untangling that context after the fact is the only way to see the pattern at all. It's a genuinely strange result, but a well-replicated one, and it says something real about how quantum information is structured, even if it doesn't license the more dramatic claim that the future changes the past. A related and equally strange phenomenon is called the quantum Zeno effect, named after the ancient Greek philosopher Zeno, known for his paradoxes about motion. In quantum mechanics, this effect refers to the fact that frequently measuring a quantum system can actually freeze its evolution, preventing it from changing at all. This was predicted theoretically in the late 1970s and confirmed experimentally in the early 1990s in experiments where physicists trapped ions and watched how repeated measurements affected their evolution between energy states. The way it works is this: a quantum system, left alone, will gradually evolve from one state into a superposition involving another state according to the Schrödinger equation. But if you measure the system very frequently, each measurement has a tendency to reset the system back toward its original state, because measurement collapses the system onto one of its possible outcomes. And if you check often enough, that outcome is overwhelmingly likely to still be the starting state, since not enough time has passed for much change to accumulate. The counterintuitive result is that watching a quantum system closely enough can prevent it from changing, an effect that has since been demonstrated clearly in laboratories using trapped atoms and photons, and has even found practical uses in certain quantum error correction schemes. Together, these experiments point toward the same underlying lesson as the basic double-slit result, but sharpen it considerably. The behavior of a quantum system isn't simply determined by some hidden, pre-existing state that exists independently of measurement. It depends, in ways that are precisely predictable, mathematically, but still philosophically puzzling, on the full structure of what information gets recorded, preserved, or erased, and even on how often a system is checked. Quantum mechanics doesn't just describe particles. In some sense, it describes the relationship between systems and the process of finding things out about them, and that relationship turns out to be woven into physics far more deeply than the classical picture of the world ever suggested. This is exactly the puzzle that's often called the measurement problem, and it's one of the genuinely open questions in the foundations of physics. Different interpretations of quantum mechanics answer it differently, as we touched on earlier, and there is no experimental way currently known to distinguish between them. What all of this experimental work has firmly established, though, is that the strangeness isn't a matter of poor equipment or sloppy theorizing. It's a robust, repeatedly confirmed feature of how the universe behaves at small scales, one that no purely classical, common-sense picture of solid objects moving through space has ever been able to accommodate. Let's step back from individual experiments for a moment and ask a more basic question. What are particles, according to our best current theories? The intuitive picture, still common in everyday language, treats electrons and photons and quarks as tiny solid balls, like miniature marbles. But that picture was already abandoned by physicists roughly a century ago, replaced by something considerably stranger and, in its own way, more elegant. The modern framework is called quantum field theory, and it underlies what's known as the Standard Model of particle physics, developed gradually through the middle of the 20th century, with major contributions from physicists including Richard Feynman, Julian Schwinger, Shinichiro Tomonaga, and many others, and largely completed in its current form by the 1970s. The Standard Model successfully describes three of the four known fundamental forces: electromagnetism and the strong and weak nuclear forces, along with every known type of fundamental particle, except for the graviton, the hypothetical particle that would carry the force of gravity. In quantum field theory, the basic building blocks of reality aren't particles at all. They're fields, continuous entities that exist at every point in space, rather like an invisible medium filling the entire universe. There's an electron field, a photon field, fields for each type of quark, and so on. What we call a particle is not some separate object moving through this field. It's a localized excitation, a ripple or a disturbance in the underlying field itself. A useful, if imperfect, way to picture this is to imagine a perfectly still pond. If nothing disturbs it, the pond is calm and featureless. But if you toss a stone in, a ripple spreads outward, a temporary, localized pattern of disturbance, moving across the otherwise calm surface. In quantum field theory, a photon is something like that ripple, but in the electromagnetic field, rather than in water, and an electron is a ripple in the electron field. These fields fill the entirety of space, everywhere, all the time. And what we detect as individual particles are the specific, quantized ways these fields can vibrate. This picture explains something that puzzled physicists for a long time: why every electron in the universe is completely identical to every other electron, with exactly the same mass, exactly the same charge, exactly the same properties, no matter where it came from or how it was produced. If electrons were tiny individual objects, manufactured somehow, you might expect at least tiny variations between them, the way no two handmade objects are ever perfectly identical. But if every electron is simply an excitation of the same underlying electron field, which exists everywhere and behaves according to the same fixed rules everywhere, then of course every electron looks identical. They aren't separate objects that happen to resemble each other. They're the same kind of disturbance in the same field, appearing in different places. One of the more remarkable predictions of quantum field theory concerns what happens in a supposedly empty region of space, a vacuum with no particles present at all. Classically, you'd expect a vacuum to simply be nothing, calm and featureless, with zero energy, but quantum field theory predicts that even in a perfect vacuum, the fields are never perfectly still. They undergo constant small fluctuations, governed by the same uncertainty that governs particles, and these fluctuations can be thought of loosely as pairs of particles and antiparticles winking briefly into existence and then annihilating each other again, borrowing energy for an instant before paying it back, consistent with the constraints of quantum uncertainty. This isn't just a mathematical curiosity. It has measurable physical consequences. One of the clearest is called the Casimir effect, predicted by the Dutch physicist Hendrik Casimir in 1948. Casimir showed that if you place two uncharged, perfectly conducting metal plates extremely close together in a vacuum with a gap of only a few hundred nanometers, the plates will experience a tiny attractive force pulling them together, even though there's no charge, no matter, and no obvious classical mechanism to explain it. The effect arises because the plates restrict which vacuum fluctuations can exist in the narrow gap between them compared to the space outside, creating a slight imbalance in the pressure exerted by these fluctuations from each side. This tiny force was first measured with reasonable precision in a laboratory in 1997 by the physicist Steve Lamoureux, and has since been confirmed with high accuracy in numerous subsequent experiments. The empty vacuum of space, it turns out, is not simply nothing. It's a quietly active, fluctuating structure, even when there's no matter present at all. This has a further consequence worth sitting with. If particles are just excitations of underlying fields, then the sharp boundary we normally imagine between this object and empty space around it starts to blur. An atom is mostly, by volume, empty space, in the sense that its nucleus and electrons occupy only a tiny fraction of the region we draw a boundary around when we say, here is the atom. What we experience as the solidity of matter, the resistance you feel when you push your hand against a table, isn't really matter colliding with matter in any literal sense. It's electromagnetic fields generated by the electrons in your hand and the electrons in the table, repelling each other before the underlying particles ever get close. Solidity, in other words, is a large-scale effect that emerges from electromagnetic field interactions among a huge number of atoms, not a fundamental property of some tiny hard core sitting at the center of matter. None of this means matter isn't real, or that objects don't genuinely exist in some meaningful sense. Tables and hands and stars are all real, describable, measurable physical systems, but the modern physical picture of what makes them up looks nothing like the intuitive picture of tiny solid balls bouncing around in empty space. It's fields everywhere, all the time, occasionally rippling into the localized, quantized disturbances we call particles, embedded in a vacuum that is itself subtly, measurably active rather than simply empty. This raises a further question, one that takes us out of the world of particles and fields entirely and into the structure of space itself. If fields fill all of space, What is space exactly? Is it simply a fixed backdrop that fields and particles move through the way a stage exists independently of the actors performing on it? Or is space itself something that emerges from a deeper structure in much the way that particles turned out to emerge from fields? That question takes us into one of the strangest and most actively researched areas in all of theoretical physics: the connection between gravity, black holes, and information. In the early 1970s, physicists studying black holes ran into a puzzle that would eventually reshape how many of them think about space itself. A black hole, according to general relativity, is a region where gravity is so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. For a while, black holes were treated as simple objects, describable with just a few numbers: mass, electric charge, and rotation. But in 1972, the physicist Jacob Bekenstein, then a graduate student, proposed something that seemed strange at the time. He suggested that a black hole should have entropy, a measure of the amount of hidden internal information or disorder within it, and that this entropy should be proportional not to the black hole's volume, as you might expect for an ordinary object, but to the surface area of its event horizon. This was met with skepticism initially, including from Stephen Hawking, who worked out the mathematical details more rigorously and initially argued against Bekenstein's proposal. But in 1974, Hawking discovered something remarkable in his own calculations. Black holes aren't actually completely black. Due to quantum effects near the event horizon, they should slowly emit a faint form of radiation, now called Hawking radiation, and as they do, they should very gradually lose mass and eventually evaporate over spans of time that, for realistic black holes, would vastly exceed the current age of the universe. This calculation confirmed that black holes do indeed have a genuine physical temperature and entropy, essentially vindicating Bekenstein's proposal. Together, this is now known as the Bekenstein-Hawking entropy formula, and it precisely relates a black hole's entropy to the area of its event horizon, not its volume. This led to a genuine paradox, one that occupied physicists for decades, and in certain technical respects, still generates active debate today. Quantum mechanics has a deep principle built into it called unitarity, which essentially guarantees that information is never truly destroyed, only ever transformed or scrambled. Whatever falls into a system, in principle, the details of what it was should still be recoverable in some scrambled form from the system's later state. But if something falls into a black hole, and the black hole eventually evaporates away entirely through Hawking radiation, where does the information about what fell in actually go? Hawking's original calculation suggested it might simply be destroyed, which would violate one of the deepest principles of quantum theory. This became known as the black hole information paradox, and it drove an enormous amount of theoretical work from the 1970s onward, including a famous scientific wager between Hawking, the physicist Kip Thorne, and the physicist John Preskill about whether information really is lost, a bet Hawking eventually conceded in 2004, agreeing that information is likely preserved after all, encoded somehow in the outgoing radiation, though the precise mechanism remained mysterious for years afterward and is still being actively refined using newer techniques. The fact that a black hole's information content scales with its surface area rather than its volume turned out to be an important clue about something much bigger than black holes alone. In the early 1990s, the physicist Gerard de Hooft proposed an idea that came to be called the holographic principle, later developed further by the physicist Leonard Susskind. Their proposal was that this pattern, information scaling with surface area rather than volume, might not be a quirk specific to black holes. It might be a general feature of any region of space that includes gravity, the complete physical information describing what happens inside any three-dimensional volume of space might, in principle, be fully encoded on the two-dimensional boundary surrounding that volume, like a hologram, where a flat two-dimensional surface can store enough information to reconstruct a full three-dimensional image. This idea moved from an intriguing conjecture to something with real mathematical teeth in 1997, when the physicist Juan Maldacena, then working on string theory, discovered a precise and remarkable mathematical relationship, now called the anti-de Sitter, and conformal field theory correspondence, usually abbreviated as the ADS and CFT correspondence. Maldacena showed that a particular kind of theory, including gravity, defined in a certain type of curved space, is mathematically equivalent to a completely different kind of theory, one with no gravity at all, defined only on the lower dimensional boundary of that space. Calculations done in the gravitational theory, involving curved space-time and objects moving through it, give exactly the same answers as calculations done in the boundary theory, which involves no space-time curvature and no gravity whatsoever, just particles and fields living on a flat lower dimensional surface. This has become one of the most influential results in theoretical physics over the past few decades, because it suggests very concretely in this particular mathematical setting that a space-time with gravity can be thought of as arising from or being equivalent to information encoded on a boundary with one fewer dimension and no gravity at all. It gives physicists an actual working toolkit, not just a philosophical suggestion, for exploring the idea that space and gravity might be emergent phenomena arising from a more fundamental description involving information and entanglement. It's worth being careful about the scope of this result. The precise version of the ADS and CFT correspondence that Maldacena proved applies to a specific, mathematically convenient type of space-time, one with a particular kind of negative curvature, which is not the same as the actual space-time we live in. Our universe appears to have a slight positive curvature associated with its accelerating expansion, a different geometric setting where an equally precise version of this correspondence hasn't yet been established. So, while the holographic principle, in its general form, is taken seriously by many physicists as a plausible feature of quantum gravity, the specific mathematical proof we have is, for now, a proof about a simplified toy model of the universe, not a proof about our actual universe, extending the idea rigorously to a universe like ours, one with the kind of positive curvature associated with accelerating cosmic expansion, remains an active and unfinished area of research. Still, the broader implication has stuck and reshaped how many physicists think about the deep questions in this field. If information about a gravitational system can, at least in some precise mathematical settings, be fully captured by a description with one fewer spatial dimension and no gravity at all, then space and gravity themselves start to look less like fundamental ingredients of reality and more like something that emerges from a deeper layer, built out of information and its structure. That single realization opened the door to an entire research program trying to understand exactly how space might arise from something even more basic, patterns of quantum entanglement. If space really does emerge From something more fundamental, the natural next question is, emerge from what? Over the past couple of decades, one of the leading answers physicists have explored is quantum entanglement itself. The same strange correlations we talked about earlier in the context of Bell's theorem. In 2010, the physicist Mark van Ramstonk wrote an influential paper making a striking argument using the mathematical tools of the ADS and CFT correspondence. He showed that if you take the boundary description of one of these model universes and gradually reduce the amount of entanglement between different regions of that boundary, the corresponding gravitational space-time on the other side doesn't just get modified, it starts to tear apart, disconnecting into separate pieces, push the entanglement all the way down to zero, and the space-time doesn't just become distorted, it stops existing as a single connected geometry at all. Van Ramstonk's conclusion was that the connectivity of space-time itself, the very fact that one point in space is near another point in space, might be built directly out of the pattern and degree of quantum entanglement between the corresponding parts of the boundary description. Entanglement, in this view, isn't just a strange quantum phenomenon happening inside space-time. It might be the stitching that holds space-time together in the first place. A closely related and even stranger proposal came in 2013 from Juan Maldacena, whom we met earlier as the discoverer of the ADS and CFT correspondence. Working together with Leonard Susskind, they proposed what's now called the ER equals EPR conjecture, playfully combining two ideas that had, until then, seemed completely unrelated. The ER refers to a 1935 paper by Einstein and the physicist Nathan Rosen describing a theoretical structure in general relativity called an Einstein-Rosen bridge, more commonly known today as a wormhole, a hypothetical tunnel-like connection between two distant points in space-time, or even between two separate universes. The EPR refers to the Einstein, Podolsky, and Rosen paper we discussed earlier about entangled particles. Maldacena and Susskind's proposal was that these two ideas, entanglement and wormholes, might actually be two different mathematical descriptions of the exact same underlying physical connection. In certain precisely defined theoretical models, they showed that a pair of entangled black holes can be described equally well as connected by a wormhole through space-time, or as simply sharing quantum entanglement with no geometric connection at all, and that these two descriptions give consistent, equivalent physical predictions. The suggestion is that entanglement between any two quantum systems might be intimately related to, or possibly identical to, some kind of geometric connection between them, even when that connection isn't visible in any ordinary sense. It's an active and still not fully settled area of research, but it has become one of the most productive ideas in modern theoretical physics for exploring how space-time geometry and quantum entanglement might be two faces of the same underlying structure. Around the same period, the Dutch theoretical physicist Eric Verlinde proposed a different but related idea in a 2010 paper, suggesting that gravity itself might not be a fundamental force at all, but instead an emergent phenomenon similar to how temperature and pressure emerge from the statistical behavior of enormous numbers of molecules without being fundamental properties of any single molecule on its own. In Verlinde's proposal, gravity arises from how information is distributed across surfaces in space related to entropy, and the familiar force of gravitational attraction shows up as a kind of statistical, thermodynamic tendency of the underlying system, rather than as a basic force carried by its own fundamental particle. This idea, often called entropic gravity, remains a minority position among physicists working on quantum gravity, and it has faced significant challenges from certain astronomical observations, particularly related to the behavior of galaxy clusters, that some researchers argue are difficult to reconcile with Verlinde's specific models. It remains an active but contested research program rather than an established or widely accepted result. A different, and in some ways more radical, approach to the question of emergent space comes from a research program called loop quantum gravity, developed from the late 1980s onward, with major contributions from physicists including Abhay Ashtekar, Carlo Rovelli, and Lee Smolin. Rather than starting from the ADE and CFT correspondence, or from string theory more broadly, loop quantum gravity attempts to quantize general relativity directly, and in doing so, arrives at a picture in which space itself is not smooth and continuous at the smallest scales, but discrete, built up out of tiny, indivisible units, connected in a structure called a spin network, essentially a web of relationships and quantum states. In this picture, if you could zoom in far enough past a length scale known as the Planck length, roughly 1.6 times 10 to the negative 35th of a meter, space wouldn't look like an infinitely smooth continuum at all. It would dissolve into a discrete, granular structure, and what we experience as smooth, continuous space at everyday scales would be an approximation that emerges only when you zoom back out, averaging over an enormous number of these tiny fundamental units, much the way a smooth, continuous-looking photograph on a screen is actually built from a grid of discrete pixels, invisible individually at ordinary viewing distance. Loop quantum gravity and string theory, which underlies the ADS and CFT correspondence, are, in an important sense, rival research programs built on different foundational assumptions, and physicists working in each camp do not agree on which, if either, correctly describes reality. Neither has yet made a testable prediction that clearly distinguishes it from the other or from alternative approaches, largely because the energy scales where quantum gravity effects would become directly detectable are far beyond what any current or currently planned experiment can reach. Both remain serious, mathematically sophisticated research programs actively pursued by thousands of physicists worldwide, but neither should be described as an established, confirmed theory of nature. They are competing hypotheses about how space, time, and gravity might ultimately fit together with quantum mechanics, and the question of which approach, if any, turns out to be correct remains genuinely open. One more idea worth mentioning here, because it connects the physics of emergent space to a broader philosophical shift in how some physicists think about reality, comes from Carlo Rovelli, one of the founders of loop quantum gravity, who has also developed a distinct interpretive framework called relational quantum mechanics. First proposed in a 1996 paper, Rovelli's proposal is that quantum properties don't belong to a system in isolation. They only make sense relative to some other system that's interacting with it or measuring it. In this view, there's no single, absolute, view-from-nowhere description of what a particle is doing. There's only a description relative to a particular observer or physical system, and different observers interacting with the same particle in different ways may correctly describe it differently without either description being more fundamentally true than the other. This is a genuinely minority interpretation among physicists, one of several competing frameworks for making sense of the measurement problem we discussed earlier, but it's had a meaningful influence on how some researchers think about the deep connection between information, relationships, and the structure of space and time. Taken together, these different research threads, entanglement and emergent spacetime, the holographic principle, loop quantum gravity, relational quantum mechanics, don't yet add up to a single, agreed-upon picture of what space fundamentally is, but they share a common thread, one that shows up again and again across very different mathematical approaches. Space, in a growing number of serious theoretical frameworks, looks less like a fixed, fundamental backdrop that things move through, and more like something that arises from a deeper layer of relationships, correlations, and information, becoming visible to us only at the scales we're used to living our lives at. So far, we've mostly talked about space, but time turns out to raise an even stranger set of questions, ones that sit at the heart of unresolved attempts to unify quantum mechanics with general relativity. In everyday experience, time feels like the most obvious, undeniable thing there is. You remember the past, you anticipate the future, and there's a clear sense of one moment following another. But when physicists tried to combine quantum mechanics with general relativity into a single framework, describing the quantum state of the universe as a whole, something strange happened to time in the resulting equations. In 1967, the physicists Bryce DeWitt and John Wheeler derived what's now called the Wheeler-DeWitt equation, an attempt to describe the wave function of the entire universe using the combined mathematical machinery of quantum mechanics and general relativity. One of the most discussed features of this equation is that it contains no explicit time variable at all. Ordinary quantum mechanics describes how a system's wave function changes over time using an equation with a time variable built directly into it, called the Schrödinger equation. The Wheeler-DeWitt equation, applied to the universe as a whole, simply doesn't have that variable. It describes relationships between different possible configurations of the universe, but nothing in the equation itself ticks forward the way an ordinary clock does. This is often called the problem of time in quantum gravity, and it remains an open, actively debated question in theoretical physics, rather than a solved puzzle. One proposed resolution, developed by physicists including Don Page and William Wouters in the early 1980s, suggests that time, as we experience it, might emerge from correlations between different parts of a fundamentally timeless quantum state, in much the way we discussed space, potentially emerging from patterns of entanglement. On this view, one part of the universe can serve as a kind of internal clock relative to another part, and what we experience as the flow of time is really just the correlation between the state of that internal clock and the state of everything else, rather than time being some independent, ticking background parameter that exists on its own. This is sometimes called the Page-Wouters mechanism, and while it's a serious and mathematically developed proposal, it remains one hypothesis among several, not a settled resolution to the problem of time. There's a separate, more empirically grounded reason. Physicists suspect that our everyday sense of time's flow isn't quite as fundamental as it feels, and this one comes from thermodynamics rather than quantum gravity. The basic laws of physics, at the level of individual particle interactions, are almost entirely symmetric with respect to time. If you took a video of two billiard balls colliding and played it in reverse, the reversed video would still obey the same underlying laws of motion just as well as the original. There's nothing in the fundamental equations of motion that says balls have to collide and separate in one particular time direction rather than the other. This is true for the vast majority of known physical laws, including Newton's laws, Maxwell's equations for electromagnetism, and the equations of quantum mechanics itself, when applied to individual particles or small systems. And yet, our everyday experience of time is deeply, obviously asymmetric. Eggs break and don't spontaneously reassemble. Coffee cools down and doesn't spontaneously heat back up while cooling the room around it. Memories point toward the past, never the future. This large-scale asymmetry is captured by the second law of thermodynamics, formalized in the mid-1800s by physicists, including Rudolf Clausius, and later given a deeper statistical foundation by Ludwig Boltzmann, which states that in an isolated system, entropy, a measure of disorder, or the number of ways a system's microscopic details could be arranged while looking the same at a large scale, tends to increase over time, not decrease. The puzzle, which Boltzmann himself grappled with in the 1890s, is why entropy should reliably increase in one direction at all, given that the underlying microscopic laws don't prefer one time direction over the other. The generally accepted answer, though its deeper justification remains an active area of research and discussion among physicists and philosophers of physics, is that the universe simply began near the Big Bang in an extraordinarily low entropy state, meaning an extraordinarily orderly, improbable starting configuration, and everything we experience as the forward flow of time is really just the universe's steady, statistically overwhelming drift from that special, low entropy starting point toward higher entropy, more probable configurations. On this view, the arrow of time we experience isn't built into the fundamental laws of physics at all. It's a large-scale, statistical consequence of the particular, unusually low entropy conditions the universe happened to start with. Some physicists connect this thermodynamic picture back to quantum mechanics and quantum information theory more directly, suggesting that the emergence of a definite, classical-looking sequence of events, the kind of orderly cause and effect we experience day to day, might itself be tied to the way entanglement spreads and grows within a large, complex system over time, transitioning it from behaving in strange quantum ways toward behaving in familiar classical ways as more and more particles become entangled with their surroundings, a process called decoherence, which we'll come back to a little later because it turns out to be one of the more important and less mysterious explanations for why the everyday world looks solid and classical, even though it's built from strange quantum ingredients underneath. The overall picture that emerges from all of this, though it remains genuinely unsettled in its details, is that time, much like space, may not be as fundamental a feature of reality as it feels from the inside. Some of our best mathematical frameworks for describing the universe as a whole don't contain an explicit time parameter at all, and the felt experience of time passing may be better understood as an emergent, statistical, or relational phenomenon arising from entropy, entanglement, and correlation, rather than as a basic ingredient that was there from the very beginning, ticking away on its own, independent of everything else. By this point in the story, a pattern has shown up again and again. Particles turn out to be excitations of fields. Space seems tied to patterns of quantum entanglement. Time may be an emergent statistical feature rather than a fundamental one across many different areas of physics. When researchers dig down looking for some solid, independent foundation underneath, they keep finding relationships, correlations, and structure rather than simple, independently existing stuff. This pattern led the physicist John Wheeler, whom we've already met a few times in this story, to propose a memorable phrase in a paper from 1990, summarizing decades of thinking on the subject. It from bit, Wheeler's suggestion was that every physical thing, every particle, every field, every measurable quantity might ultimately derive its existence from something more basic, discrete, yes or no answers to questions, essentially binary distinctions or bits of information arising through the process of observation and measurement. In Wheeler's own framing, this was meant somewhat poetically and provocatively as a way of expressing his conviction that information and observation play a far more fundamental role in physics than the older picture of a purely material universe made of independently existing stuff would suggest. It's worth being clear about what kind of claim this is. It from bit is best understood as a philosophical framing or a research heuristic meant to point physicists toward a certain way of thinking about foundational questions rather than as an established physical theory with clear testable predictions of its own. Wheeler himself was a deeply respected physicist who made concrete, well-established contributions to general relativity and nuclear physics. But this particular phrase belongs to the more speculative, foundational end of his thinking, an invitation to reconsider what's truly fundamental, rather than a settled scientific conclusion. This general direction of thinking, sometimes called digital physics or information theoretic physics, has been developed further by various researchers in different and not always compatible directions. One prominent example is the work of the physicist and computer scientist Stephen Wolfram, who has argued, particularly in a large research effort he calls the Wolfram Physics Project, launched publicly in 2020, that the fundamental laws of physics might arise from very simple computational rules applied repeatedly to abstract mathematical structures called hypergraphs, essentially networks of connections without any inherent notion of space built in. Wolfram's team has shown that applying certain simple rewriting rules to these abstract graphs over and over can generate structures that display some features reminiscent of known physics, including certain aspects of relativity and quantum behavior. This is an ambitious and mathematically serious research program, but it remains at this point a proposal and a set of preliminary explorations rather than an established or widely accepted theory among the broader physics community, and it hasn't yet produced a clear, testable prediction that distinguishes it experimentally from existing physical theories. A different and, in its own way, even more sweeping proposal comes from the physicist Max Tegmark, who has argued for what he calls the mathematical universe hypothesis, developed most fully in a 2007 paper and a later book. Tegmark's claim is that physical reality isn't merely described by mathematics the way most physicists would put it, but that physical reality simply is a mathematical structure, and that every logically self-consistent mathematical structure exists in exactly the same sense that our own physical universe exists. On this view, our particular universe isn't uniquely privileged. It's just one among an enormous, perhaps infinite, collection of mathematical structures that are all, in some sense, equally real. This is a striking and philosophically ambitious idea, but it's important to say plainly that it remains a minority position, even among physicists interested in foundational questions, and it isn't testable in any way currently known, since by its own logic, it would apply equally to any mathematically consistent universe, including ones that look nothing like our own. It's worth pausing here to separate physics from philosophy a little more carefully than pop science treatments of this topic sometimes do, because the phrase, "the universe might be a simulation," tends to get physics and philosophy tangled together in a way that can be misleading. The philosopher Nick Bostrom, in a well-known 2003 paper, made a purely probabilistic argument, not a physics argument, about simulated realities. His reasoning goes roughly like this: if it's technologically possible for sufficiently advanced civilizations to run detailed simulations of conscious minds, and if at least some civilizations that reach that level of technology choose to run many such simulations, then simulated conscious beings would vastly outnumber non-simulated ones, purely as a matter of counting. If that's true, Bostrom argued, then a randomly selected conscious observer, not knowing anything else about their situation, should assign a fairly high probability to being one of the simulated ones, rather than one of the rare, original, non-simulated ones. This is an interesting argument in the philosophy of probability and self-location, and it has generated substantial philosophical discussion and debate. But it is not a physics result. It doesn't rest on any specific finding from quantum mechanics, general relativity, or any experimental result we've discussed so far. Some popular treatments of this topic borrow findings like Bell test violations, the holographic principle, or discreteness at the Planck scale, and present them as evidence supporting Bostrom's argument specifically, but this connection is largely an interpretive and rhetorical one, not a scientific inference that most physicists working on these topics would endorse. The physics we've covered, entanglement, holography, emergent spacetime, discreteness at very small scales, is genuinely well supported and, in many cases, experimentally confirmed. Whether any of it specifically supports the idea that we live inside a simulation, in Bostrom's sense, built by some other civilization, is a separate, much more speculative claim, one that most physicists regard as interesting to think about, but essentially untestable with current or foreseeable technology. What does seem to be a genuinely durable and widely shared observation, even among physicists who are skeptical of stronger claims like Tegmark's or Bostrom's, is that the universe, at a fundamental level, behaves in ways that are strikingly well described using the language of information, discrete states, precise, exactly repeatable rules, and quantities like entropy that measure information content directly, whether that means the universe fundamentally is information in some deep metaphysical sense, or whether it just means that information theory happens to be an extremely powerful and useful mathematical language for describing physical law, is a genuinely open question, one that sits closer to the philosophy of physics than to an experimentally settled result. It's a question worth holding lightly, with curiosity rather than certainty, because right now, nobody, however accomplished, actually knows the answer. Let's return now to the measurement problem we introduced earlier, because there's one more thread to follow, and it's probably the most philosophically charged part of this whole story. The question of what role, if any, a conscious observer plays in all of this. Here's the shape of the puzzle again, stated a little more carefully. Quantum mechanics describes systems using a wave function, a mathematical object representing a superposition of possible outcomes. When a measurement happens, we observe one definite outcome, not a blend of several. The equations of quantum mechanics, on their own, don't include a built-in mechanism that says exactly when or how this transition from superposition to a single definite outcome actually happens. This gap is what's called the measurement problem, and it has genuinely puzzled physicists since the theory's earliest days. One important and often underappreciated piece of this puzzle has actually been resolved, or at least substantially clarified, since the theory's early years, through a process called decoherence, worked out in detail mainly from the 1970s through the 1990s by physicists, including Heinz-Dieter Zeh and Wojciech Zurek. Decoherence explains, in a mathematically precise way, why large systems, made of enormous numbers of particles, essentially never display quantum superposition effects like interference in practice, even though the underlying theory technically allows it. The reason is that any realistic large system is constantly interacting with its surrounding environment, countless air molecules, stray photons, thermal vibrations, and each of these interactions subtly measures the system in a sense, causing different parts of its superposition to become entangled with different environmental states. Once that happens, the different possible outcomes lose the ability to interfere with each other, even though, in the most complete mathematical description, all of them technically still exist within an enormous, combined superposition involving the system and its environment together. From the point of view of anyone looking only at the system itself, without tracking every last detail of its environment, the system appears to have settled into one definite classical-looking outcome, even though nothing has technically collapsed in the most literal reading of the underlying equations. Decoherence is well established, experimentally verified, and widely accepted among physicists as an accurate description of why large systems behave classically, even though they're built from quantum ingredients. What decoherence does not fully resolve, and this is the part that remains genuinely contested, is why we experience one single definite outcome at all, rather than experiencing ourselves as existing in some kind of superposition alongside all the other possible outcomes. Decoherence explains why interference effects between different outcomes become practically unobservable once a system becomes sufficiently entangled with its environment. It doesn't, by itself, explain why our conscious experience seems to pick out just one of those outcomes as the one that actually happened, rather than all of them simultaneously. This remaining puzzle is sometimes phrased as the difference between the when of the disappearance of interference, which decoherence answers quite well, and the why just one outcome of subjective experience, which it doesn't directly address at all. Different interpretations of quantum mechanics answer that remaining question in different ways. As we discussed earlier, Many Worlds says all outcomes really do happen in separate, non-interacting branches, and there is no unique, the one that happened, only a branch you happen to find yourself continuing in. Copenhagen-style interpretations tend to treat the question as not being well posed in the first place, and other interpretations offer still other answers. This is where the physicist Eugene Wigner, in the 1960s, introduced a thought experiment that pushed the question of the observer's role even further, now generally known as Wigner's friend. Imagine a friend of yours, alone in a sealed laboratory, performing a quantum measurement, say, checking the spin of a particle, which could come out as either up or down. From your friend's point of view, once they look at the result, the measurement seems complete and definite. They see one outcome, and as far as they're concerned, the wave function has collapsed. But if you, standing outside the sealed lab, describe the entire situation using the full mathematical machinery of quantum mechanics, Without yet having opened the door to ask your friend what they saw, the theory technically requires you to describe your friend, along with the measured particle and the entire laboratory, as existing in a superposition of both possible outcomes at once, friend having seen up and friend having seen down, combined together until you yourself interact with the system by opening the door. This creates an apparent contradiction. From the friend's internal perspective, the measurement is already definite and complete. From your external perspective, before you check, it's still described as an unresolved superposition. Wigner originally used this thought experiment to argue that consciousness itself might play a necessary, physically fundamental role in causing wave function collapse, suggesting that perhaps the friend's own conscious awareness of the result was what truly collapsed the wave function for real, and that an unconscious recording device wouldn't have the same effect. It's important to know that Wigner himself later grew skeptical of this particular conclusion, and most physicists working in the field today do not treat consciousness causes collapse as an established or even leading explanation. What's genuinely fascinating and worth knowing about is that in recent years, this thought experiment has moved from pure philosophy into the realm of actual laboratory tests. In 2019, a team led by the physicist Massimiliano Proietti carried out an experimental version of an extended Wigner's friend scenario using multiple entangled photons to play the roles of the observer and the friend in a carefully controlled optical setup. Their results confirmed that the strange, seemingly contradictory perspectives described in the thought experiment really do show up experimentally, in the sense that a Bell-like inequality involving both perspectives can genuinely be violated, similar in spirit to the original Bell test violations we discussed earlier. This is a real, meaningful experimental result, actively discussed in the physics community, showing that quantum mechanics doesn't allow for a single, universally agreed upon fact about what happened that holds equally for every observer in every situation. However, and this is important to say clearly, this experimental confirmation does not demonstrate that consciousness has any special causal role in the process. The observer and friend in these experiments are photons and optical devices, not conscious beings at all, and the striking result concerns the logical structure of how different physical systems can consistently disagree about outcomes, not any special power of awareness itself. Most physicists interpret these results as reinforcing the idea that facts about measurement outcomes may be relative to the observer or physical reference frame involved, connecting back to the relational quantum mechanics we discussed earlier, rather than as evidence that consciousness specifically causes quantum collapse in some unique, physically privileged way. There's a further, related idea worth mentioning honestly as a genuinely fringe position within physics, even though it circulates widely in popular discussions of this topic. The notion, sometimes called panpsychism or analytic idealism when developed philosophically, that consciousness might be fundamental to reality rather than something that merely emerges from complex physical arrangements like brains. A related, more formal framework from neuroscience called integrated information theory, developed primarily by the neuroscientist Giulio Tononi starting in the mid-2000s, attempts to give a mathematical definition of consciousness based on how much integrated information a system generates, in principle allowing consciousness to be assigned, in theory, to any sufficiently integrated physical system, not just brains. Integrated information theory remains a genuinely contested framework within neuroscience and the philosophy of mind, with serious researchers on multiple sides of the debate. Some see it as a promising formal approach to a notoriously difficult problem, while others have raised significant technical and conceptual objections to it, including concerns about whether its mathematics genuinely captures anything specifically related to conscious experience. As opposed to structural complexity more generally, it is not a settled or majority position in neuroscience, and it should not be confused with an established finding within physics itself, even though it sometimes gets folded into popular discussions of quantum consciousness as if it were closely connected to results like the Wigner's friend experiments. The two lines of research, quantum foundations on one hand and theories of consciousness on the other, remain largely separate, and any deep connection between them remains speculative, genuinely interesting to think about, but far from established. What we can say, honestly, and without overclaiming, is this: quantum mechanics has never fully resolved what role, if any, the observer plays in bringing about a definite outcome, and careful experiments continue to reveal that different observers, in a well-defined technical sense, may not be able to agree on a single, universal account of what happened, at least not without additional communication between them. That's a genuinely strange and unresolved feature of the deepest theory we have. Whether it says anything at all about the nature of consciousness itself remains an open question, one where enthusiasm has, at times, run considerably ahead of the actual evidence. Let's shift scale entirely now, away from particles and measurement, and out toward the largest structures in the universe, because it turns out that cosmology, the study of the universe as a whole, has its own set of deep, unresolved puzzles, and they connect back to some of the same foundational questions we've been exploring since the 1920s, thanks initially to the observational work of the astronomer Edwin Hubble. We've known that the universe is expanding, distant galaxies are moving away from us, and the further away a galaxy is, the faster it appears to be receding, a relationship now called Hubble's law. For most of the 20th century, the expectation was that this expansion should be gradually slowing down over time due to the mutual gravitational attraction of all the matter in the universe pulling against the expansion. Then, in 1998, two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, studying the light from distant exploding stars called Type 1, a supernova, found something unexpected. The expansion of the universe isn't slowing down, it's speeding up. This discovery, which earned the three researchers the Nobel Prize in Physics in 2011, implied the existence of some kind of pervasive, mysterious energy filling all of space, causing this accelerating expansion. Physicists now call this dark energy, and based on current cosmological measurements, it appears to make up roughly 68% of the total energy content of the universe. But calling it dark energy is really just giving a name to our ignorance. We can measure its overall effect on cosmic expansion quite precisely, but we don't currently have a confirmed, agreed-upon physical explanation for what it actually is. The simplest mathematical description of dark energy, and the one that fits current observations best overall, is something called the cosmological constant, a term Einstein himself originally introduced into his equations of general relativity back in 1917 for entirely different reasons, related to trying to build a static, unchanging model of the universe. Before Hubble's discovery of cosmic expansion made that motivation obsolete, Einstein later reportedly described adding this term as one of his biggest blunders, though historians of science have noted that this famous quote may be somewhat exaggerated or apocryphal. Ironically, it turned out decades later that something very much like this term might be needed after all, just for a completely different reason than Einstein originally had in mind, not to keep the universe static, but to explain why its expansion is accelerating. Here's where things get genuinely strange, in a way that's considered one of the deepest unsolved problems in all of physics. Quantum field theory, the framework we discussed earlier for describing particles as excitations of underlying fields, predicts that empty space, the vacuum, should have its own inherent energy, arising from the constant quantum fluctuations we talked about earlier in connection with the Casimir effect. If you try to calculate the expected value of this vacuum energy using quantum field theory and compare it to the actual amount of dark energy we observe astronomically, the two numbers disagree by an almost unimaginable margin, roughly a factor of 10, followed by around 120 zeros. This mismatch is often called the cosmological constant problem, and it's frequently described as the worst prediction in the history of physics, precisely because the discrepancy is so extreme. It strongly suggests that something important is missing from our understanding, some deep principle or cancellation mechanism that prevents most of this predicted vacuum energy from actually gravitating the way our naive calculation assumes it should. But nobody currently has a broadly accepted explanation for what that missing piece actually is. A separate mystery, discovered even earlier, involves what's called dark matter, starting in the 1930s with early observations by the astronomer Fritz Zwicky, and developed much further in the 1970s through the detailed work of the astronomer Vera Rubin and her collaborators studying the rotation of spiral galaxies. Astronomers found that galaxies rotate in a way that doesn't match the amount of visible matter, stars, gas, and dust that we can actually see within them. Based on the visible matter alone, the outer regions of galaxies should be rotating much more slowly than they actually do. The gravitational pull of the visible matter alone simply isn't strong enough to hold them together at the speeds observed. The leading explanation, though still not directly confirmed through the actual detection of whatever particle might be responsible, is that galaxies are embedded within much larger, invisible halos of some additional form of matter, which doesn't interact with light in any way we can currently detect, but which does interact gravitationally, providing the additional mass needed to explain the observed rotation. Based on current cosmological measurements, dark matter appears to account for roughly 27% of the universe's total energy content, considerably more than the roughly 5% made up of ordinary, familiar matter, the atoms that make up stars, planets, and everything we're directly familiar with. Considerable effort, spanning decades, has gone into trying to directly detect whatever particle might constitute dark matter using highly sensitive underground detectors designed to catch the extremely rare interactions such particles might have with ordinary matter. As of now, no such particle has been directly and conclusively detected, despite increasingly sensitive experiments, which has led some physicists to explore alternative explanations, including modifications to the law of gravity itself at very large scales, an approach generally called modified Newtonian dynamics, though this alternative approach faces its own significant challenges in explaining certain other astronomical observations, particularly involving colliding galaxy clusters and remains a minority position compared to the standard dark matter explanation among cosmologists and astrophysicists. There's one more puzzle worth mentioning here, smaller in scale but genuinely interesting. Certain features observed in the cosmic microwave background, the faint, pervasive glow of radiation left over from roughly 380,000 years after the Big Bang, when the universe first became transparent to light. Extremely precise measurements of this background radiation, particularly from the European Space Agency's Planck satellite mission, which operated through the early 2010s, have revealed a few subtle, statistically modest anomalies. Certain unusually cold or unusually aligned regions of the sky that don't perfectly match the simplest theoretical predictions. These anomalies are real in the sense that they show up consistently in the data, but they are statistically modest, meaning they're the kind of thing that could plausibly arise from ordinary statistical fluctuation. Given how many different features of the data have been examined, rather than necessarily pointing toward new physics, most cosmologists currently treat these anomalies as interesting curiosities worth continued monitoring with future data rather than as clear evidence of anything dramatically wrong with our overall picture of the universe's early history. Though a minority of researchers continue to investigate whether they might hint at something more significant, taken together, these cosmological puzzles, dark energy, dark matter, and the cosmological constant problem mean that, according to our best current measurements, roughly 95% of the total energy content of the universe consists of components we don't have a confirmed, fundamental physical explanation for. That's a genuinely humbling fact, and it's worth sitting with for a moment. It doesn't mean our physics is wrong, in the sense that the mathematical frameworks we have make extraordinarily precise, repeatedly confirmed predictions across an enormous range of phenomena. But it does mean that the deep nature of most of what fills the universe remains, quite literally, unknown, an open frontier rather than a settled chapter, and one that connects, in ways still being worked out, to some of the questions about space, time, and information that we've spent this whole evening exploring. Let's bring this back down to something more personal for a while, because everything we've discussed so far, fields instead of particles, entanglement instead of solid distances, and emergent rather than fundamental flow of time, naturally raises a question about you specifically. If matter, space, and time are all looking less fixed and fundamental than they used to, what does that mean for the sense that you are a single, continuous, stable thing moving through all of it? Biologically speaking, your body is far less stable than it feels. The cells that make up your body are constantly dying and being replaced. Different tissues turn over at different rates. Some cells, like most neurons in your brain, last your whole life, while others, like the cells lining your gut or the outer layer of your skin, are replaced within days or weeks. Even the individual atoms making up your body are gradually exchanged for new ones over the years as you eat, breathe, and metabolize. In a very literal, physical sense, very little of the actual material making up your body today was part of you a decade ago, and yet you experience yourself as continuous, as the same person you were then, with a thread of memory and identity running through all of that physical turnover. This puzzle isn't new to modern physics at all. Philosophers have wrestled with versions of it for a very long time, going back at least to ancient Greek discussions of the ship of Theseus, a thought experiment, asking whether a ship remains the same ship after every one of its planks has gradually been replaced over time. What's changed is that neuroscience and physics have added considerable empirical detail to an old philosophical question without fully resolving it. Neuroscience adds its own layer of complexity here. The sense of having a single, unified conscious experience, sometimes called the hard problem of consciousness, a phrase coined by the philosopher David Chalmers in 1995, remains one of the most difficult open problems bridging science and philosophy. It's relatively straightforward, at least in principle, to study how the brain processes information, how neurons fire, how different brain regions coordinate activity. These are what Chalmers called the easy problems of consciousness. Easy only in the sense that they're the kind of thing neuroscience has clear tools and methods to investigate. Even if the actual research is difficult and ongoing, the genuinely hard problem is explaining why any of that physical processing should be accompanied by subjective experience at all. Why there's something it's like to see the color red or taste something bitter, rather than all that information processing simply happening in the dark, with no inner experience attached to it whatsoever. Nobody currently has a broadly agreed upon scientific explanation for this, and it remains an active area of philosophical and scientific debate without a clear resolution in sight. This is where some physicists and philosophers of physics have started drawing connections back to the observer dependence we discussed earlier in quantum mechanics, though it's worth continuing to be careful about how strong a connection to draw. One serious, relatively modern approach is called cubism, short for quantum Bayesianism, developed primarily by the physicist Christopher Fuchs, starting in the early 2000s, along with collaborators including Rudiger Schack and David Mermin. Cubism proposes that the quantum wave function shouldn't be thought of as describing some objective feature of the world that exists independently of any observer. Instead, it should be understood as describing a particular observer's personal degrees of belief or expectations about what they'll experience in future measurements, similar in spirit to how probability is understood in a certain school of thought within statistics called Bayesian probability, where probabilities represent an individual's rational degree of belief rather than an objective frequency existing out in the world. On this view, when the wave function collapses upon measurement, nothing physically dramatic is actually happening out in the world at all. What's happening is that a particular observer is updating their own personal expectations in light of new information they've just gained, the same way you'd naturally update your expectations about anything else after learning something new. Cubism is a serious, actively developed interpretation of quantum mechanics, discussed and debated within the physics community. But like the other interpretations we've mentioned, it remains one contested position among several, not a consensus view. Critics of cubism argue that it risks making physics seem like it's only about individual belief, rather than about an external, shared reality that different observers are all, in some sense, trying to describe together, and the debate between cubism's defenders and its critics remains lively and unresolved. A related, though distinct, idea comes from John Wheeler again, late in his career, in what he called the participatory universe, or participatory anthropic principle. Wheeler's suggestion, expressed in a memorable phrase, was that no phenomenon is a real phenomenon until it is an observed phenomenon, meaning that the universe, in some sense, requires observers, acts of measurement and observation in order for definite physical facts to come into being at all, rather than the universe existing as a complete, definite, fully detailed structure independently of any observation ever taking place within it. This is a genuinely provocative philosophical position, one that Wheeler explored seriously and returned to throughout the later decades of his career. But it remains speculative in the sense that it isn't a claim that can currently be tested experimentally in a way that would clearly distinguish it from alternative interpretations where the universe does have definite properties independent of observation. They simply aren't accessible to us without measurement. It's worth noting, since it's sometimes brought up in popular discussions of these topics, that some of these ideas about identity being relational rather than fixed, about the self being a process rather than a static, unchanging thing, echo certain themes found in various philosophical and contemplative traditions developed independently long before modern physics, including certain strands of Buddhist philosophy that describe the self as a constantly changing process rather than a fixed, permanent entity. These are genuinely interesting parallels worth knowing about and thinking carefully about, but it's worth being cautious about treating them as though modern physics has somehow scientifically validated a particular religious or philosophical tradition. The parallels are suggestive and worth genuine reflection, but the physics itself, the measurement problem, entanglement, decoherence, developed through entirely independent lines of mathematical and experimental work, and connecting it too tightly to any particular older philosophical tradition risks overstating what the physics actually establishes on its own. What we can say, carefully, is this: modern physics has made the question, what is a stable, persistent object really, considerably more subtle than it used to seem, whether we're talking about an electron, a person, or the universe as a whole. Whether that subtlety ultimately supports deep, specific philosophical conclusions about the nature of the self, or whether it simply reflects the fact that our everyday concepts of object and identity were built for a world of medium-sized, slow-moving things, and were never going to map perfectly onto the deep structure of physical reality at its most fundamental level, remains an open and genuinely interesting question, one without a settled answer, and quite possibly one that different people, thinking carefully about the same physics, will continue to answer differently for a long time to come. Given everything we've covered, it's worth spending some time on what's actually happening right now in laboratories and observatories around the world, because none of this is purely historical. These are active, ongoing areas of research with real experiments planned or already underway, trying to push on exactly the questions we've been discussing. One of the more direct approaches involves trying to test whether gravity itself has quantum properties, something that hasn't yet been demonstrated experimentally, even though it's assumed by most approaches to quantum gravity. In 2017, two independent groups of physicists, one including Sugata Bose and collaborators, and another including Chiara Marletto and collaborators, proposed a clever experimental approach, now often called the Bose-Marletto proposal. The idea is to place two small but massive objects, tiny crystals containing embedded quantum spins, into quantum superpositions of being in two different locations at once, and then let their mutual gravitational attraction act on them while they're in superposition. If gravity has quantum properties, the proposal predicts that the two objects should become entangled with each other purely through their gravitational interaction, with no other force involved. If gravity turns out to be fundamentally classical, meaning it doesn't support quantum superposition and entanglement the way other forces do, no such entanglement should appear. This experiment hasn't yet been successfully performed at the sensitivity required because it demands extraordinary precision in isolating the test masses from other, much stronger sources of interference. But multiple research groups around the world are actively working toward the technical capabilities needed to attempt it, and it represents one of the few currently proposed experiments that could give a direct, laboratory-based clue about whether gravity is quantum in the same sense as the other fundamental forces. Quantum entanglement experiments themselves have also continued to push toward larger and larger scales. In 2017, Chinese researchers using a satellite named Michius demonstrated entanglement distribution between ground stations separated by over 1,000 kilometers, sending entangled photon pairs from orbit down to 2 separate locations on Earth, and confirming that Bell inequality violations still held over that distance, extending the kinds of tests Alain Aspect and others had performed decades earlier over much shorter distances. This research continues, both as a test of the fundamental limits of quantum entanglement and as a practical step toward quantum communication networks and, eventually, more secure methods of transmitting information. Quantum computing itself, while primarily a technological pursuit rather than a foundational physics experiment, has an interesting relationship to some of the questions we've discussed. Quantum computers being actively developed by companies and research institutions including Google, IBM, and various university and government labs operate using quantum bits, or qubits, that can exist in superpositions and become entangled with each other, exploiting exactly the strange quantum properties we've spent this whole conversation discussing. As these machines become more capable, they offer physicists an increasingly powerful, controllable laboratory setting for directly testing and exploring quantum phenomena, including some of the entanglement and information theoretic ideas connected to the holographic principle and emergent spacetime that we discussed earlier. Several research groups have used quantum computers and quantum simulators to construct small-scale, simplified analogs of wormhole-like behavior predicted by the ER equals EPR conjecture, though these remain simplified proof-of-concept demonstrations within highly controlled, small quantum systems, not evidence about the structure of actual spacetime in our universe. On the cosmological side, several major observational projects are either underway or planned specifically to sharpen our understanding of dark energy and dark matter. The Vera C. Rubin Observatory, a large ground-based telescope in Chile, named after the astronomer whose work helped establish the case for dark matter, began its main survey operations in the mid-2020s and is expected to map billions of galaxies over the coming years, providing much more precise measurements of how galaxies are distributed and how that distribution has changed over cosmic history, data that should help constrain both dark matter and dark energy considerably more tightly than before. The European Space Agency's Euclid Space Telescope, launched in 2023, is conducting a similarly ambitious survey specifically designed to measure the effects of dark energy and dark matter on the large-scale structure of the universe with high precision. Meanwhile, proposed future gravitational wave observatories, including a space-based mission called LISA, planned for launch in the 2030s by the European Space Agency in partnership with NASA, aim to detect gravitational waves at frequencies inaccessible to current ground-based detectors like LIGO and Virgo, potentially offering new windows onto extreme gravitational environments, including the mergers of massive black holes that could provide further tests of general relativity in regimes where quantum gravitational effects might, in principle, leave subtle traces. There's also continued work searching for direct evidence of quantum gravitational effects at the smallest observable scales, though this remains extremely difficult given how far beyond current technology the relevant energy scales are. Some researchers have proposed looking for very subtle effects using extremely high energy cosmic rays or gamma ray bursts, checking whether light of different energies traveling across billions of light years arrives at slightly different times, which could be a signature of a granular, discrete structure of space at very small scales, the kind predicted by loop quantum gravity and some other approaches. Instruments, including the Fermi Gamma Ray Space Telescope, have been used to search for exactly this kind of effect. So far, no clear evidence of this kind of energy-dependent travel time has been found, which places increasingly tight constraints on certain specific models of quantum gravity without yet ruling out the broader research program. It's worth being honest about the overall state of affairs here. Despite this genuinely impressive and ongoing experimental effort, quantum gravity remains, at present, a theoretical framework without direct experimental confirmation. String theory, loop quantum gravity, and the various other approaches we've touched on tonight remain competing research programs, each internally consistent and mathematically sophisticated in its own way, but none of them has yet produced a clear, distinguishing experimental prediction that's actually been tested and confirmed. This isn't a failure of the physicists working on these problems. It largely reflects just how extraordinarily difficult it is to probe physics at the scales where quantum gravity effects are expected to become significant, scales far beyond what any particle accelerator or telescope currently available or currently planned can directly access. It may simply be that definitive answers to some of tonight's deepest questions are still decades away, waiting on technologies we haven't yet built, or on some unexpected observational clue nobody has thought to look for yet. So, after everything we've walked through tonight, what can we actually say, carefully and honestly, about whether the universe is real in the way it seems? We can say that your everyday perception, the colors, sounds, and textures that make up your conscious experience, is genuinely constructed by your nervous system, a simplified, useful model built from raw sensory signals, not a direct window onto whatever is happening underneath. That much is well-established neuroscience, even if stronger claims about perception being entirely disconnected from an underlying reality remain a matter of ongoing debate among cognitive scientists and philosophers of mind. We can say that quantum mechanics, tested with extraordinary precision for about a century now, describes a world where particles don't have definite properties independent of measurement, at least not in the way classical physics assumed, and where distant entangled particles show correlations that can't be explained by any theory respecting both locality and realism together, a conclusion confirmed decisively through decades of increasingly careful experiments, recognized with a Nobel Prize in 2022. What exactly this means, philosophically, about the nature of reality underneath our observations remains genuinely disputed among serious physicists through several competing interpretations that all agree on the mathematics and all disagree about what that mathematics is actually telling us about the world. We can say that particles, in our best current theories, aren't tiny solid objects at all, but localized excitations of fields that fill the whole of space, and that even a supposedly empty vacuum turns out to be subtly, measurably active. We can say that black holes, information, and the structure of space-time seem to be connected in a deep way, one captured mathematically by the holographic principle, and that patterns of quantum entanglement may be intimately related to, or perhaps even responsible for, the very connectivity of space itself, though the precise, complete version of this idea, extended fully to a universe like ours, remains an unfinished piece of theoretical work. We can say that time, similarly, might not be a fundamental ingredient built into the universe from the start, but something that emerges from entropy, correlation, and change, a possibility suggested by several independent lines of research, though, again, without full agreement on the details. We can say that questions about the role of the observer in quantum mechanics remain genuinely unresolved. That decoherence explains a great deal about why the everyday world looks solid and classical, while leaving open a deeper question about why we experience one definite outcome rather than a superposition of all of them. We can say that recent experiments testing extended versions of the old Wigner's friend thought experiment have shown that different observers, in a precise technical sense, may not be able to agree on a single universal account of events without communicating with each other first, a genuinely strange and confirmed result. And we can say, just as clearly, that none of this currently supports strong claims that consciousness itself causes quantum collapse, or that the universe is definitely a simulation, or that integrated information theory has solved the hard problem of consciousness. Those remain live, contested, minority positions, interesting to think about, worth taking seriously as open questions, but not settled science. However often they get presented that way in popular treatments of this subject, and we can say that cosmology has its own humbling admission to make. Roughly 95% of the universe's total energy content in the form of dark matter and dark energy remains fundamentally unexplained, even as our measurements of its overall behavior grow more and more precise with each passing year. Put all of that together, and what you get isn't a single, tidy conclusion that the universe doesn't exist, or that it's all an illusion, or that physicists have secretly proven reality is fake. What you get is something quieter and, in its own way, more genuinely interesting. A picture of nature in which many of the things that feel most solid and self-evident from the inside, solid objects, a smooth, continuous space, a steadily ticking flow of time, a single agreed-upon set of facts shared identically by every observer, turn out, on careful examination, to rest on deeper, stranger, less intuitive foundations, fields instead of particles, entanglement instead of simple separation, emergence instead of fixed fundamentals, relationships, in a very real mathematical sense, doing more of the foundational work than the things we thought were being related. None of this means nothing is real. It means that real is a more layered word than it feels like in ordinary life, and that the deepest layers physics has managed to uncover so far look less like solid ground and more like a structure of consistent, precisely measurable relationships, holding together with remarkable stability, even without an obvious, final bedrock underneath. There's still an enormous amount left to learn. Physicists don't yet know how to fully unite quantum mechanics and gravity into a single, tested theory. They don't yet know what dark matter and dark energy actually are, only how they behave on large scales. They don't know how to resolve the measurement problem in a way that would satisfy everyone, or whether such a resolution is even possible given our current mathematical tools. They don't know whether space and time are truly emergent in our own universe, the way certain toy models suggest, or whether that idea will eventually run into some obstacle nobody has spotted yet, and they don't know how to bridge the gap between physical description and subjective experience. The hard problem of consciousness in any way that feels genuinely settled. What they do have is an enormous, carefully built structure of mathematics and experiment, refined over more than a century, that makes extraordinarily accurate predictions across scales ranging from the inside of atoms to the edge of the observable universe, even while leaving some of the very deepest why and what is it really questions open. That combination, extraordinary predictive precision paired with genuine, humble uncertainty about the deepest foundations, is not a weakness of physics. It's closer to what makes it worth continuing to study at all. If everything were already settled, there would be nothing left to discover, and clearly, judging by everything we've walked through tonight, there is still a great deal left to discover. So, when you hear sometime that scientists are suggesting the universe might not be real, or might be information, or might not exist independently of an observer, you'll know now roughly where that idea comes from, which parts of it rest on solid, repeatedly tested experimental ground, and which parts remain genuinely open, argued over by careful, serious people who don't yet agree, and who are, in their own quiet, patient way, still working on it. Maybe the most honest way to leave things tonight is exactly where the story keeps leaving us, not with a final answer, but with a genuinely well-earned sense of wonder about how strange and how carefully, patiently knowable the world keeps turning out to be. One careful measurement at a time, somewhere, right now, in a laboratory with the lights left on late into the night, someone is running one more version of an old experiment, tightening one more measurement, checking one more assumption most people never think to question, and the universe, whatever it ultimately turns out to be, space or field or information or something we don't have a word for yet, keeps quietly, patiently allowing itself to be measured a little more precisely, one experiment at a time. That's where we'll leave it for tonight.